Okay, welcome to the next class on multiple view geometry. This class we will actually tackle the reconstruction problem. We will try to recover the motion of the camera and the 3D scene from two views. We have all the basics that we need for that. We talked about how to model the camera motion, the rigid body motion that consists of rotation and translation. We talked about how to mathematically model the projection process, how to get 3D coordinates onto the image plane, the perspective projection in particular. And we talked about how to determine point correspondences. So if you have two consecutive images, say, and something moves or the camera moved, how you find the correspondence from one image to the next. Now we have all that, so we will tackle the reconstruction problem, and I want to start by actually defining what I mean by reconstruction problem. As usual, we make assumptions. I mentioned that before in image analysis. Whenever you tackle a problem, problems are difficult and you need to make certain assumptions. To start with, here we make three main assumptions. The first assumption is that we are given a set of corresponding points. So we in two images taken from the same camera, with the same camera from different viewpoints. So we assume we observe a scene, we take two images, and we assume someone gives us for a set of points the correspondence. How many points we actually need, we'll talk about that in a second, but a certain number of points where we know these are in correspondence. This is a strong assumption. In reality, you don't have that correspondence, but we assume that somehow someone has an algorithm that can compute it, so now we have some correspondence. In reality, the truth is that you have to estimate that correspondence, and it may not be correct. And in fact, some of the reconstruction algorithms only work well under the assumption that the correspondences are correct. There are two issues that can happen in real world when you have correspondences. One is that for a point pair, a pair of corresponding points, the correspondence is slightly off, meaning it is there but not exactly in that location but nearby. The second thing that can happen is that you have substantial outliers, that a pair that is assumed to be corresponding doesn't actually correspond. That it's not that they're slightly off, but it's the wrong partner. For example, if you image a checkerboard pattern, you're going to have these the intersections of the different patches. You will have the same one in multiple locations, and then you might identify a correspondence that is not the right one. So these are two errors that can happen. For now, we just assume we have the right correspondence for a set of points. And we'll talk later about what to do in cases that this correspondence is not correct, not accurate. Secondly, we assume that the scene is static. It's not moving, it's not dynamic. That means from one image to the next, the scene didn't actually move, the 3D points stayed where they are. To some extent, you can loosen this assumption by saying, well, if the whole scene moves and the camera moves, it doesn't matter. What's important is that somehow the relative motion is what matters. But the assumption is that if the scene moves, then all points move in the same way, with the same rigid motion. But, you know, so that is exchangeable. Of course, whether I move the whole scene or whether I move the camera is equivalent with respect to the images, comes out to the same. So for now, we assume a static scene. And in addition, we will assume that the intrinsic camera parameters are known and fixed. So that means from one image to the next, we not only assume it's the same camera, but we assume that the user didn't fiddle with the focal lengths or you know, change the zoom settings or whatnot. So all the intrinsic parameters we talked about, the focal lengths, the radial distortion, etc., we assume all of these were estimated beforehand, they're known, and so you can basically remove them in some way. You can normalize everything so that these parameters don't play a role. These are assumptions, and of course, you know, the most general reconstruction problem does not match with these assumptions. The most general reconstruction problem that we would like to solve is, of course, reconstructing actions, reconstructing dynamic scenes where things change, reconstructing scenes where I zoom in, I zoom out, and still the algorithm can recover 3D. This is difficult, and so we will start with making these assumptions, and through the course of the lecture, we will see where we can relax these assumptions. For example, we say maybe the scene is not static, but piecewise static, or piecewise rigid, if you will. That you have maybe a static background and some object that moves rigidly, and then you have two kinds of motions. One is the camera motion, and one is that rigid object motion. And we'll see you can also do things for these scenes. But for now, let's work with these assumptions. As always in research, you make assumptions, and my suggestion to anyone starting doing his own research project is always start with a lot of assumptions. Start with very strong assumptions that constrain your solution. And once you have a solution, once you showed under these assumptions I can do something, then you can see how to relax these assumptions gradually. That's usually a good way to go. What I often see is students come up, they say, I want to solve this project, and they tackle a very complex project. They want to estimate everything in one, and then they start implementing and it doesn't work. They don't get solutions, and then they're disappointed. And so usually it's better to constrain your problem sufficiently so that you know, I'm going to get a solution. And once you have that solution, you know, generalize from there. The way we do it, once we tackle this problem, and maybe I'll make a little drawing that's going to come up multiple times in this class. The idea is that you have the 3D scene here. You have points in that 3D scene that you observe from different viewpoints. And for now, we will assume the two-view case. So we assume that points are visible in two images. And what we don't know and what we want to estimate is the external camera parameters, that is the rotation and translation, the rigid body motion from one camera center to the other. And what we also don't know is the 3D location of our points. We call them large X. So X is a vector in R3, and we will call these projections X1 and X2. These are the 2D projections of that 3D point in the two images, little x because they're 2D. In practice, we will use homogeneous coordinates, meaning they also have three components. The third one is 1. And as you see, the problem has two sides. We need to estimate the motion of the camera, and we need to estimate the 3D location of points. And actually, this is a nasty chicken and egg problem, in the sense that if I know the camera motion, then it's trivial. All I have to do, I have the corresponding points, right? Assume someone tells you this is how the camera moved. And that's actually not unrealistic. If you have a camera that has inertial sensors on it, gyroscopes, anyone in the smartphone has that GPS inertial sensors, they can actually estimate the camera motion for you. And if that motion is sufficiently accurately estimated, you have it. So you don't need to look at the images, you look at GPS sensors or inertial sensors to estimate that motion of your camera. Maybe someone magically through other sensors gives you that camera motion. Then all you need to do is triangulate these rays, and where they intersect, that's your 3D location. So you're done, and that's actually quite trivial to do. In turn, if someone tells you what the 3D location of these points are for multiple points, then you can actually estimate the camera motion. Find a camera motion such that these rays actually go through these points. And there's only one solution typically for that if you have enough points. And so either of the two problems, knowing the other, is easy to solve. The key challenge in reconstruction is you don't know the camera motion and you don't know the 3D locations. If you know one, you can estimate the other, vice versa, and vice versa. The question is, how do I get both? And this is the challenge, and there is one interesting approach to it that we will pursue in this class, and that is to first estimate the camera motion, and once we have the relative location and orientation of the camera, translation, rotation, then reconstruct the 3D location of points. The fascinating thing is this is a chicken and egg problem, but there are ways to decouple the problem, and we will see in this class today how to do that. Here is the scenario again with two real images. So you stand on the marketplace, and this is a common scene. You've all had that. You take one picture from that building, you take another picture, and you see clearly these are different viewpoints. There are parts of the scene that are not visible in the other image, but there are typically lots of points that I do see in both images. And then I have some point, let's call it P here. This is large X in this drawing, is the 3D location of that point. And then I see that point in the two images. I'll call these locations X1, little x1, and little x2. And we call the camera centers O1 and O2, O for origin. That is where the center of the camera is. And remember, the perspective projection is such that you just take the ray from the 3D point through the camera center, and where it intersects the image plane, that's your 2D location. So this is the two-view scenario. Mind you, we will spend a lot of time on the case of two views. But of course, in general, we will have the 3 or M-view scenario, where if you have a moving camera, you see lots of images of that same scene. And we will see later how the algorithms that we derived for two views, how they can be generalized to the multi-view setting. Maybe some more notation. So here's again a more schematic drawing. This is the point in 3D. Here are the origins of the camera. We can connect these origins, so we can define a line here that connects these 2 points, and that line connects these 2 points, and that line intersects the image planes. Both of these image planes in this drawing, it intersects them in the visible area. That doesn't need to be. If the cameras are fairly parallel, then maybe the intersection is outside the viewable domain, but it doesn't matter. What's important is that this image plane, if you extend it infinitely, at some point it intersects. Similarly here, at some point it intersects. These points where it intersects are called the epipoles. E1 for the first image and E2 for the second image. These are the epipoles. In addition, we have these lines that connect the 3D point to the origin. And here's the intersecting point. That is the 2D coordinate of that point in the second and the first image. And the connecting lines between the epipoles and that 2D point is called the epipolar line. So in two images, I have two epipolar lines. And this whole plane here, spanned by the two camera centers and the 3D coordinate, is called the epipolar plane. So a lot of terminology. It's just so you've heard these terms. I put everything on one slide so you can always go back to that slide. If you don't remember what was the epipolar plane, what was the epipolar line, here you have it all. What's important is there is an epipolar plane associated with each possible 3D point. Right? If I vary that 3D point large x, I get different epipolar planes spanned by that point and the two camera centers. And so these are some of the notations underlying what's called epipolar geometry. Sorry, the epipolar lines are these here. The lines connecting the epipoles and the 2D coordinates. So there's two epipolar lines. I call them L1 here and L2. This is important and interesting because, for example, if you connect the 2D coordinate in the first image to the second camera center, then seen from that camera, the corresponding point is somewhere on the epipolar line. Something that people who work on stereo reconstruction know, that you search for correspondences along the epipolar lines. Yes?
Maybe that the line 01, 02 doesn't intersect both image planes, right? For example, if one camera is right behind the other one.
Yes. There are degenerate cases. I said there's always an intersection, but possibly it's at infinity, right? If there's no rotation between the cameras, then you get the degenerate case where the line is parallel to the image planes, and then you have an intersection at infinity. You can imagine if you have a little bit of rotation, there's always an intersection, but if you reduce the rotation, that intersecting point goes to infinity. Yeah, so that indeed can happen in the case of absence of rotation. How would you solve the reconstruction problem? It's actually quite easy to formalize the reconstruction problem, to write down a cost function in order to solve it. And what you do there, and this is quite common for solving any research problem, any parameter estimation problem. A lot of problems in science are problems of estimating parameters, and you can tackle these by defining a cost function that tells you for any set of parameters whether this is a good set or a bad set of parameters. Here, for example, what do we want? Let's say we have these 2D coordinates, x1 and x2, the 2D coordinates of point J. So we assume we have points that are numbered with the index J, say maybe 100 points. So here the sum goes from 1 to 100. So we have 100 points that we observe in image 1 and in image 2. We don't know what these points are, so these are unknowns. So we have 100 3D vectors that are unknown. This is x1 through x100. In addition, we have rotation and translation of the camera unknown. These are another 6 parameters. Remember, 3 parameters to model the rotation and 3 for the translation. So in total, the number of unknown parameters is quite large. We have 100 times 3 coordinates, so that would be 300 parameters plus 6. 306 parameters that we have to estimate. A lot of parameters. That means if you tackle the problem in terms of optimization, you are working in a 306 dimensional space. It's not good usually. But nevertheless, what we have are the 2D coordinates. What we need to estimate are the 3D coordinates and the camera motion. And now what do? We say, well, find parameters in such a way that the projection of these 3D points to 2D matches the observation in the first camera, which basically means that we put ourselves in the coordinate system of the first camera. So with respect to, we try to find coordinates in the coordinates of the first camera such that if I project them down, they should match. And remember, that is just the generic projection that divides by the third component. Yes?
We are subtracting the projected point from 2D point. Can we do inverse? Can we back project the 2D point?
No. Yes, that's a good question. Can we back project? Can we work in 3D? Yes. There are different ways to parameterize this objective function. This is one way to parameterize it. There are many others we'll see later. This is a good point. There are different ways. For example, you can also, instead of estimating the 3D locations, you can try to estimate the true 2D location that would be consistent as opposed to the observed 2D location. So here, what this minimizes is what's called the projection error. We want to find a model of the scene, meaning the 3D locations of points, and the camera motion in such a way that once I project the 3D points down to 2D, I want to be not equal to the 2D coordinates, but as close as possible to them. So we minimize the distance. The way you can see that is I estimate some 3D location, large X, and once I project it down, I get this projection, and I want to minimize the discrepancy here. It should be as close as possible to the observed 2D location. So this is the error that we minimize. This is that distance here, and we minimize the square. We don't have to minimize the square. You may recall I mentioned this earlier. There are many ways to set up a cost function. Whether you square it or don't square it is a matter of, you know, preferences. There are different ways to represent that. Here, what I wanted to write here, this is a shorthand notation. What it means is I have to take for the second image, this is the observed coordinate in the second image, I have to transform that 3D point into the coordinates of the second image. So this is Rx plus t, essentially. And then I project down again. So basically it means if I transform into the coordinates of the second camera, then do the generic perspective projection, I should match the observation in the other image. And so this would be a way to formalize the reconstruction problem, find a reconstruction, camera motion, 3D locations, such that it matches the observations as best as possible. And once you say as well as possible or in the best way, there is a question of how do you measure discrepancies. And here, in a least squares sense. You don't have to do least squares, but this would be one way to penalize deviations from the observation. The problem with this is an approach which is known as bundle adjustment. It's called bundle adjustment because you have these bundles that are defined by the camera center and the 2D coordinates, and you try to adjust them in such a way that you get a consistent solution. This is called bundle adjustment. It's quite popular. It's an important strategy, an important approach. The key problem with it is it's not convex. And remember, if you have an optimization problem that is not convex, and if you have a very high dimensional problem, that's not good. It means chances are you will not find a solution. Chances are you will not find an algorithm to actually determine the solution. And to be honest, this is the state of the art. We don't know today how to solve this problem optimally. There are no optimal solutions to this problem, and this is why we are currently still doing a lot of research to try to find the best strategy to solve this problem. And there is no unique solution today, no one that everyone agrees on what would be the best way to solve this problem. So over the last years, we've seen always new approaches, new strategies to solve this problem. There are two complementary, in some sense, or competing approaches, I should say, to tackle this problem. One is to stick with that cost function and say, this is the cost function I want to minimize, and then devise sophisticated algorithms to somehow find good minimizers, where good hopefully means the optimum, but you don't know. And so there are strategies like linearization, coarse to fine, where you estimate maybe with a few points on a coarse scale, you estimate some camera motion, some 3D locations, and then you add new points and you refine, and then you hope that somehow this leads to the right solution. And sometimes, if you're not happy, you can reinitialize, you can initialize randomly and hope that with a good initialization you get a better solution. But you can imagine it's not an easy challenge. The alternative, and this is something we want to look into in this class a little more, is to try to come up with different cost functions. Cost functions that are somewhat similar, that also try to find a good reconstruction, but that are easier to minimize. They're not going to minimize the projection error in the least square sense as here, but they're going to also minimize some kind of deviation, and they will lead to cost functions that can be solved optimally. And in fact, what we will see is that we can decouple that problem. It's a chicken and egg problem because we have to estimate camera motion and 3D location. And what I wanted to show you today is that there is a way to decouple this problem. To estimate the camera motion first without the 3D locations, and then estimate 3D in a second run. This is a bit magical at first glance because these parameters are really coupled in this cost function here, and it's not obvious how to separate them, but we'll see that it can be done. And the key ingredients are the so-called epipolar constraint and then the so-called 8-point algorithm. Here's how that works. So let's start again. We know that x1, this is the 2D location in the first image in homogeneous coordinates, so the third component is 1. And we know that it corresponds to some 3D point large x, so that would be in the coordinates of the first camera, that 3D point here. We assume that the camera parameters are known. In fact, we will assume that the intrinsic camera matrix is just the unit matrix, meaning everything is in coordinates of, is in units of the focal lengths, etc. So we can ignore that intrinsic parameter matrix. Since we assume we are in the coordinates of the first camera, there's actually no rotation and translation, and so the equation is simply this one. So you see we have lambda 1 x1 is large x, right? The perspective projection is nothing but the division by the third component. Lambda 1 models that third component. Once we go into the coordinates of the second, which means that this length here, by the way, this here is lambda 1. And this length is 1. So, so if you want to get from that 3D point, let me remove that. From that 3D point to this point, you just scale by lambda 1. If we go into the second camera, we call this lambda 2. That is the distance of the 3D point from the second camera center. Then we have to get into the coordinates of the second camera, and that is done by rotation and translation. So Rx plus T is the same 3D point, but in coordinates of the second camera. And division by lambda gives us the 2D coordinate x2. And so we have these two equations to fulfill. We need a translation rotation and a 3D location such that both equations are correct. Now I'll show you, you can reformulate these equations and gradually kick out the 3D location. We said it's a coupled problem. We have the 3D location in here and we have the camera motion in here. We want to kick out one of the two, and we will kick out the 3D location. How do we do that? Well, let's insert this equation, the large x, in here. If we do that, we get lambda 2 x2 equals r times lambda 1 x1 plus t, right? So we just inserted one equation into the other. Now we multiply by the matrix T hat. Remember, T hat is the 3 by 3 skew symmetric matrix that models the cross product with T. We can define such a matrix, so we just apply the cross product with T from the left hand side. What do we get? Why do we do that? because we want to remove that t. Remember, a vector cross product with itself is always 0, so t hat applied to t gives us 0, which means all that remains is lambda are scalars, we can pull them up front, lambda 2 t hat x2 equals, again lambda can be pulled out, lambda 1 t hat r x1. Now we can project and see what happened now is, since we inserted this equation, large X is gone. The 3D locations is no longer there. It's still there indirectly because lambda 1 and lambda 2 are the distances. These are the unknowns really, because we have the 2D location. So if we have lambda 1 x1 is the 3D location. So we still have parameters associated with the 3D location. We want to kick these out as well. How do we do that? We do scalar product of this whole thing with x2. Why is that? Well, this here is t cross x2. It's the cross product of t and x2, so it is a vector that is orthogonal to x2. Meaning if we do projection on x2, this term becomes 0. So if we do x2, multiply x2 with x2 from the left, then this term becomes 0, and this term becomes lambda 1 x2 transpose t hat r x1. And then we can divide by lambda 1. Typically this is not 0, meaning the point we observe is not in the camera center, but it's somewhere up front. And so then we get this equation. So by multiplying with x2 transpose from the left, this term becomes 0, and here we get x2 transpose t hat r x1 equals 0. And this is interesting because now we have an equation, a single equation, that couples the 2D coordinates that we observed and the camera motion t and r. There are no 3D parameters involved. So this is quite fascinating that, considering that setting of the two views, I see the same 3D point in two views that differ by rotation and translation of the camera. Considering this scenario, I can get an equation that couples the known 2D locations and the camera motion, rotation and translation. And no 3D coordinates, so they are removed here. This constraint is called the epipolar constraint. It is a constraint that couples 2D parameters that we have observed and camera parameters. And so the idea is that if we have enough of those epipolar constraints, one for each observed 3D point, then we can estimate the camera motion that is consistent with these constraints without ever considering 3D locations. Yes?
So to solve this, we need at least 6 points.
Good point. The question is how many corresponding point pairs we need. And we'll see that you need more than 1 point. Of course, how many you need, we'll get into that later. The first algorithm I'll present is called the 8-point algorithm because it assumes knowledge for 8 points. How many you really need to solve this problem is a separate question. It's a somewhat difficult problem, and in fact it boils down to 5 points. You can show that if you observe 5 points in 2 images, you can do a reconstruction, and this in fact was the result of Krupa in 1913, very old result. Yes. Yes, yes. The question is whether these equations are then all independent necessarily, right? In principle, for 6 parameters in a linear system, 6 equations would be enough. Yeah. So we'll get into that a little bit later, how to solve this problem, how to estimate translation and rotation. But it's a good point. How many points do we need? There is a trade-off in practice. Ideally, you want an algorithm that works with very few points only, because whenever you estimate correspondence, chances are you're wrong. And the fewer correspondences you need to determine, the easier. On the other hand, if you solve this for only 5-point pairs, the algorithms to solve it are very involved. And so there is some trade-off. And so, for example, the 8-point algorithm is an algorithm that says, well, assume we have it for 8-point pairs, and then we can easily solve it. In fact, often you just take more than 8 points and to get a little bit more of robustness. So this is the epipolar constraint. One should keep in mind, we did transformations to get from here to there. These transformations are not all invertible. For example, in the last step, I projected on x2. So if I take this equation, here is the same, but only those components in direction of x2. So whatever component that was orthogonal to x2 is no longer there. And similarly here, the multiplication with t hat to get from here to here is not, t hat is not an invertible matrix. So invariably, when moving from here to here, in each transformation you lose something. And this is why, once you're here, you can no longer solve this with 5-point pairs. It doesn't work, because you've already kicked out relevant information. So we lose something, but what we gain is a cost function that has no 3D coordinates. So we in some sense, from the original constraints, we derive a somewhat weaker constraint, but the advantage is that this constraint doesn't involve 3D points. It only involves the known 2D coordinates and the camera parameters. Maybe a little more about this equation. It's an important equation. It's called the epipolar constraint. Sometimes it's also called the essential constraint or the bilinear constraint, because it's bilinear. And the matrix here, T hat R, that's a 3×3 matrix. R is a 3×3 matrix, T hat is a 3×3 matrix. So this whole thing is a 3×3 matrix. This matrix is called the essential matrix E. And as I mentioned a couple of times already, as soon as things have names, in particular if they have multiple names, it tells you that this is a topic that was intensively studied by a number of people, and this is why you have different names. This is called the essential matrix, and so this is why this is sometimes called the essential constraint or the epipolar constraint. It's a relation between the 2D coordinates x1, x2 and the camera motion t and r. Unfortunately, this relation is not an easy one. You cannot directly solve for t and r. First of all, because they're coupled in this equation, in this bilinear equation, and secondly, because t and r are coupled in this matrix product. So the question is, even if you estimate E, can you get t and r from E? But before we get into how to solve this for the camera parameters, I wanted to mention a little bit about the geometric interpretation of this constraint, because it has a rather intuitive interpretation, and the interpretation I'll show you is nothing but saying that this plane spanned by the 3D point and the origins O2 and O1 is really a plane. Meaning if I take these 2D points and the vectors through them, that these rays actually intersect, which makes this form a plane and not something that is not a plane, right? If I have the two camera centers here, and then these rays, if they don't intersect, then then the whole construction doesn't span a plane. If they intersect, I have a plane. And that is exactly what this epipolar constraint states. The way we will see that is as follows. This here, this vector here is x1, right? Here is little x1, so this vector is the vector x1. Here we have 0. Now, assume we put ourselves in the coordinate system of the second camera. Then this vector, seen from the second camera, has the coordinates r times x1, because I had a rotation here. This vector has the coordinates x2 in the second camera, and this vector is proportional to the translation t, right? And so the volume spanned by these three vectors is nothing but this triple product t cross rx1 times x2. So this is rx1, this is t, so t cross rx1 times x2 is exactly defines the volume spanned by these three vectors, 1, 2, and here the third vector pointing this way. All right, so these three vectors, if I construct the triple product, it defines the volume that they span. And this volume is 0. And that is exactly what the epipolar constraint that you have above states. See, Rx1 is this here. T cross Rx1 is the same as T hat times Rx1. And x2 transpose multiplied from the left is that. So the constraint, this epipolar constraint, says nothing but the fact that the volume spanned by these three vectors is 0. Meaning that these rays actually do intersect in some 3D location. So this is why the 3D location is not actually there anymore, because the constraint says I don't care what the 3D location is, all I care about is that these rays intersect somewhere. And as soon as they intersect somewhere, it means this forms a plane. And that's what the constraint says. In other words, this constraint doesn't actually specify where the 3D location is, it just specifies there must be an intersection point. So that's the geometric interpretation. It's a little bit complicated, and it depends on how you represent the different entities. Here the idea is that you represent everything in the coordinate system of the second camera. And then you almost immediately have this epipolar constraint. A little more about this essential matrix that we have here. See, the epipolar constraint couples translation rotation in that weird matrix T hat R. This is called the essential matrix with the 2D coordinates, and the essential matrix therefore is defined by T hat times R, R being a rotation, SO3, and T being a 3D vector that is then combined into that matrix T hat. The space of all essential matrices, so all possible 3x3 matrices that you can get by combining T and R in this fashion, is called the essential space. And the reason why we want to study that essential space is because we want to estimate the essential matrix from the 2D coordinates. And once we estimate the essential matrix, we want to extract rotation and translation. So it is useful to know what do essential matrices look like, and is there a way to get rotation and translation once we have the essential matrix. And indeed, this space can be characterized. This is a theorem from 1989, Huang and Faugeras. They showed that essential matrices have a particular property. Any essential matrix, in fact this is an equivalence in the sense that E is an essential matrix if and only if we have a singular value decomposition U sigma V transpose, where the three singular values are sigma, sigma, and 0. meaning the matrix has 3 singular values, the smallest one is 0, and the 2 larger ones must be equal. This is interesting because it constrains the set of matrices that can be an essential matrix. Why is that useful? Because basically it means once I want to estimate the essential matrix, I can use that information. I can say I want some matrix E, but I know already that the 2 largest eigenvalues, singular values, must be equal, and I know also that the smallest one must be 0. So you can use that in the optimization, that property. We don't know what the singular value is. Of course, sigma can be anything. It's a positive singular value, but we know the first 2 singular values are identical, and the last one is 0. And then U and V are some orthogonal transformation involved in that singular value decomposition. So that characterizes essential matrices and this essential space. So all matrices in the essential space have that property. And in turn, any matrix that has that property is an essential matrix. The next that you can do is you can show that once we have the essential matrix, we can extract rotation and translation. Unfortunately, there is not a unique solution, but in practice there are 4 possible solutions. And I've written these down here. It looks a little bit complicated. I should be honest, I'm not going to prove that. That you have this decomposition, but because it's a bit involved, the proof, and I decided it's not so important for this class. The essential thing is that you know from the essential matrix there is a way to compute rotation and translation, and here's how you do it. You take the SVD, so once you have E, you can do an SVD, and then you have the representation U sigma V transposed. Sigma has 2 singular values being equal, the third one being 0. And then you concatenate these matrices in the following. The translation T hat for the first camera, T hat 1 for the first possible solution is U, and then a rotation around the Z axis by pi over 2, and then sigma U transposed. Maybe, if you don't remember, rotations around the z-axis, rz by an angle theta, can be written in the following: cosine theta minus sine theta, cosine theta, and then the third component is not affected. It's easy to remember. Rotations around the z-axis do not affect the z component. They preserve the z component. So this is the 3 by 3 rotation matrix that models a rotation around the z-axis. And if you have a rotation by pi over 2, it basically means that these 2 components are 0 and these are minus 1 and 1. Right? Sine of pi over 2 is 1 and cosine of pi over 2 is 0. So this is what this matrix looks like. You have the same matrix here, transpose. So it's a rotation in the opposite sense, essentially. And then you have U and V transpose. So this gives you the rotation matrix. This gives you a translation matrix. And similarly here. Sorry, I was wrong. There are 2 possible solutions, not 4. This is a rotation around the z-axis of the matrix sigma, and then it's multiplied from left and right with this matrices U. It doesn't mean that the rotation that you estimate in the end is not around the z-axis. It has nothing to do with that, because that really depends on U and V also. So as I said, I'm not going to prove this statement, but you get translation and rotation. Translation, of course, in terms of the matrix T hat, but then you can read out the three components that make up the translation vector. And so these are two possible solutions that the two possible solutions of translation and rotation for a given essential matrix. Meaning, if we can estimate the essential matrix, we can estimate rotation and translation. In practice, there are still two possible solutions, but we'll see it's actually quite easy to figure out which of the two is the right one. I just realized the settings of my display are off. I should have checked that before. I don't know why that happens. Sometimes it gets the settings wrong, and then let's see if that's better. Yes. Strange. So now how can we get from the epipolar constraint to actually doing a reconstruction? The way we do it is we've seen that the 2D coordinates of each 3D point are coupled to the camera parameters R and T through this epipolar constraint. And now how can we, the idea is basically if you have enough point correspondences and enough such epipolar constraints that you can extract the essential matrix E. And once you have the matrix E, you can estimate translation and rotation from E. What we would like to exploit is the fact that this matrix that we estimate, a 3×3 matrix E, that this matrix is an essential matrix. Remember, we had the constraints that a matrix is an essential matrix if and only if the largest singular values are equal and the smallest one is 0. There are two ways to enforce that constraint. One is that in estimating the essential matrix E from the epipolar constraints, we can estimate a matrix, just any 3×3 matrix, and then project it down to the so-called essential space. So meaning we have here the essential space, I called it E. We estimate some matrix E estimated, and then we project it down to the essential space. So some orthogonal projection onto the essential space. This is in some sense suboptimal. The optimal solution would be to optimize the epipolar constraints in the essential space, saying find a solution to the epipolar constraints under the constraint that E is in the essential space. Meaning you start with some matrix here in that essential space and then you optimize, but you make sure that you always stick in the essential space. This is in principle the better way, but in practice it's very hard to do this constraint optimization, because the constraints are on the three singular values of the matrix, and so they are very hard to enforce. And so you have a very difficult nonlinear optimization problem to solve. Whereas what we are aiming for here is some linear solution. Some solution where we can use linear algebra techniques to find the solution. And so what we will do is we will pursue the first approach. We will estimate just any random matrix E and then make sure by projection that we take the nearest essential matrix. And these are the algorithmic choices that we make to get a simple algorithm, but remember there's always a trade-off. Once you make this, you estimate some E and then you project on the essential space, you always lose something, and the question is what is the cost function that you're ultimately minimizing. And what I mentioned earlier is that it's not the reprojection error that we're minimizing here. But Doesn't matter for now. Let's work with that setting. So we estimate some matrix E, and then we project down to the essential space, which means we assure that the first two singular values are equal and the last one is 0. Here's the 8-point algorithm. This is what it's called, because we will see later it needs at least 8 corresponding points. How does it work? First of all, we rewrite this essential constraint, or the epipolar constraint. How do we do it? Here's the epipolar constraint. x2 hat e x1 is 0. We want to rewrite it in order to separate the 2D parameters in x1 and x2 with the from the camera parameters that are in the matrix E. And this is not so difficult. What we do is, see this, if you write it out, it's bilinear. This is why it's called a bilinear constraint sometimes. In particular, it's linear in the components of E. If it's linear in the components of E, there must be some way to write it as a scalar product of one vector that depends on the 2D coordinates and one vector that depends on the coordinates of E. And how is that? We just stack. This is, remember, is the stacking operation. We stack all the components of that matrix E. So these are the components. E11 to E33 are the components of the essential matrix. We just take the 3 columns of that matrix and stack them into one vector. That's the first thing we do. So here we have all the parameters of that matrix in a single vector. And then we do the Kronecker product of the 2D coordinates. So that vector A looks like that. It's a 9-dimensional vector that has all possible combinations of elements of these x, y, z vectors. And you can verify for yourself that x2 transpose E x1 is the same as A transpose E stacked. I think we even had that equality in the linear algebra session in the beginning, that we use the Kronecker product and the stacking operation to rewrite a bilinear form as a vector scalar product. Why we do that, you'll see in a second. It is to separate the unknown parameters from the known ones. Here we have the known parameters. These are the 2D coordinates in some large 9-dimensional vector. These are known, and the elements of E are the unknown ones. And that's a little bit nicer than this expression. Here we have somehow the known parameters and the unknowns are not well separated. Here we separate them just by rewriting them slightly differently. And so what we have here, this epipolar constraint now is nothing but the scalar product of 2 vectors is 0. Meaning these 2 vectors are orthogonal. That's what the constraint says. It says that if I construct a vector with the 2D coordinates, I call it A, and I take the stacked essential matrix here as a 9D vector, these 2 vectors are orthogonal. This is for one point observed in 2 images. If we do the same for a set of n points, then we can stack all these equations in the following way. Some matrix chi times E stack equals 0. Meaning the vector E stack, the unknown vector, is such that if I multiply with this matrix, it must be 0. And that matrix contains all these A's for the first point, for the second point, and for the nth point. In other words, what we've done is for each 3D point that we observe in 2 images, we just stack these 2D coordinates into this 9-dimensional vector. We do that for all points that we observe, and we have one such equation. And you see, if you take all these equations together, you can write it as a matrix vector product. So that matrix vector product contains exactly the epipolar constraints for all the endpoints together. And that means, in terms of linear algebra speaking, we can say we don't know what the essential matrix is, but the 9 components of that matrix form a vector that lives in the null space of that matrix chi. It's a vector that is mapped to 0. And so now all we need to do is look at the null space of that matrix chi, and it gives us the essential matrix. Here again we've written it, so chi times E stack must be 0, and chi contains all the 2D coordinates in this fashion for all points. So we observe n points, little n points. These are the observations of these n points in the 2 images, A1 through AN. And now we see that the matrix chi, the matrix E is such that it defines the null space of chi. And now here comes an important thought. We want to make sure that we have a unique solution. And the question is, when do we have a unique solution? When can we assure that the null space is unique? Of course, you see already is never unique. If there is a vector ES that is mapped to 0, then of course any multiple of that vector will also be mapped to 0. So there is a scale freedom here, we'll see later. And this is important, that scale freedom will haunt us through the entire class. What it amounts to is the fact that we, from 2 images alone, will never figure out the size of the baseline. There's no way to determine that. See, even if I go all the way back to the beginning here, this example, I give you these 2 images. There's no way that you can tell me how large this house is. Not from the images. Of course, as a human, you would say, hey, there's a person here. And people are like 180, 190 maybe. And then you can say, okay, if that person is 190, then I can estimate what the house is. Yeah, but you know something. You know, for one object in the scene, you know the scale. So, or at least you have a rough estimate of the scale. Of course you can use that. But who tells you that this is not a toy image and these are little puppets that look like humans but they're not, right? So you would see, I mean, this is what Hollywood works on, right? All the movies they make, at least before the computer graphics set in, they all, you know, you film a little boat in the bathtub and later it looks like a huge boat on the ocean. And the reason is that there is this scale freedom. Images themselves don't tell you the scale. And we do face that problem in practice. For example, we've devised algorithms to fly quadrocopters autonomously just using the camera. But the problem is the camera doesn't give us scale. The thing doesn't know whether this is 1 meter or 1 centimeter. Just from images it doesn't see it. So we typically need some additional sensor to give us some scale information. Say maybe an ultrasound sensor. So often in robotics you need multiple sensors because some sensors do not capture certain aspects. And the key aspect that you will never capture in a camera setting is the baseline. If I move 1 meter and the scene is 10 meters high, or if I move 10 meters and the scene is 100 meters high, comes out to the same images, exactly the same images. So there is this scale freedom, and this is what we see popping up here. Namely, that if I have an essential matrix, then any multiples of that matrix are also solutions. In practice, what you do is you typically fix the translation to be 1. Meaning in what we do, we will just say we reconstruct the scene and the camera motion such that the baseline is set as 1. In other words, we reconstruct everything in units of the baseline. That solves that problem, so you get some normalized reconstruction. And then you can always scale things to whatever. If you have some estimate of a scale, say you see a human in the scene, then you can use that and scale things accordingly. But what we want. So we have that, in addition, of course, E equals 0 is the trivial solution. That's the extreme case of scaling, right? If the translation goes to 0, everything becomes 0, the whole essential matrix is 0, you know, then... So if you shrink the whole, you know, so we have a reconstruction with camera transformation and 3D parameters that we estimate. We don't know the scale of things. If we shrink everything to a point, that's a feasible solution. That is the case that E equals 0. So of course we don't want that. So typically we normalize things appropriately. In practice, that means we want to make sure that this equation has an exactly one-dimensional null space. So as soon as there is a vector that is not null, all multiples of it are also, as soon as a vector that a non-zero vector fulfills the equation, all multiples of that vector are also solutions, but we want to make sure that the space of solutions is not 2 or 3 dimensional, but just 1 dimensional. And in that sense, once then we normalize, we will end up with a unique solution. How do we assure that this is one-dimensional? Well, you can see that it will always be at least one-dimensional. But to have an exactly one-dimensional solution, we need at least 8 point pairs. If we have 8 point pairs, then the matrix, and they're in some sense independent, we'll see later what that means, then the rank of that matrix chi is 8, and then we can expect to get a unique solution. And this is why the algorithm that I will show you in a second is called the 8-point algorithm, because it makes the assumption that I have for 8 points in the scene corresponding 2D locations. And these are these vectors A1 through A8. If you have more vectors, it doesn't hurt. So if you have more corresponding points, it doesn't hurt. But if you have fewer than 8 points, this algorithm is not going to give you a unique solution. For example, if you have 7 points, then the null space will be 2-dimensional. Even if you have 8 or more points, there are so-called degenerate cases where the solution is not unique, where the null space is not 1 but higher dimensional. A lot of these degenerate cases are somewhat, how should I say, pathological cases that do not happen in practice. There is one case, though, that happens quite frequently in the real world, and that is if all the points that you observe lie on a plane. So if all the points, say a large X that we see, if they're all on a single plane in 3D, or if they're all on a line, then we have degenerate case. In that case, it doesn't matter how many points you see, this will give you a non-unique solution, because then these vectors are not independent. It's a property that I'm not going to show you. There are more general degeneracies, so-called quadrics, etc. But as I said, these typically don't arise in practice. The issue of the plane does arise in the real world, in particular in man-made worlds. So if we go back to that scene I showed you in the beginning here, if you do reconstruction, you want to make sure that the points that you determine do not all lie on that plane. Otherwise, you have a degeneracy for the 8-point algorithm. As soon as you get points in the foreground as well, then you're fine. But if all the points lie on a plane, your 8-point algorithm will not give you a unique solution. In addition, even if we normalize E, we don't get the sign of E. So if E stack is a solution, then minus E stack is also a solution. So that sign of E we don't know, so we have two possibilities there. So once we normalize and we impose that the translation should be unit lengths, then we still have in total 4 solutions, 2 for the different signs of E, E and minus E. And then from each E, as you could see in that, we have 2 possibilities for rotation and translation, which makes a total of 4 possible configurations. In practice, it's fairly easy to find the right one. I'll get to that in a second. But first of all, I mentioned we want to do estimation, and in the algorithm we want to make sure that the matrix we estimate is an essential matrix, and so we want to make sure that we want to project down for any matrix, let's call it F, we want to find the nearest essential matrix, E. And this again I will not prove. There is a fairly easy way to project. The question is, how do you determine the distance between E and F? We want to minimize that distance over all matrices E in that essential space. If we use the so-called Frobenius norm, that means we take all elements of the matrix and just the sum of square differences. That is the so-called Frobenius norm, and the matrix E that is in the essential space that is closest to F can be easily computed in closed form. And the way it works is you do a singular value decomposition of F, get the eigenvalues, the singular values lambda 1, lambda 2, and lambda 3, where we assume lambda 1 is the largest, lambda 3 is the smallest. And then E can be determined from F by using the same singular value decomposition and simply replacing the singular values, lambda 1 to lambda 3, by sigma, sigma, and 0. And sigma is nothing but the average of the 2 largest singular values. Why that is, why this actually is the best, the essential matrix that is closest to F in the Frobenius norm, I'm not going to prove it. Which means all you have to do is, for this projection, compute the singular value decomposition and then replace the singular values in this manner. Replace the smallest one, just set it to 0, and the other 2 just average them. In addition, I should say that beforehand maybe, we said in reality we don't know the scale of things anyway. We don't know the size, so we can always multiply this with any scalar, it's still a valid solution. So what we do in practice is we set sigma to 1, meaning this is then called the normalized essential space, and the projection onto the normalized essential space amounts to taking the singular value decomposition and replacing the 3 singular values by 1, 1, and 0. The last one must be 0. The 2 larger ones must be equal. Since we can define the scale as we like it, we can just set it to 1. And so this in total gives us the so-called 8-point algorithm. I've condensed it on a single slide here. The idea is, and I should say, the 8-point algorithm is one of the core concepts in the whole class. It is the linear algorithm. It's sometimes called the linear 8-point algorithm. It allows to estimate the camera parameter directly from the 2D observed 2D points without ever looking at 3D. So here's how it works. You assume that you have 8 point pairs given in both images. Call them x1j, x1i and x2i for I equals 1 through at least 8. And then we compute an approximation of the essential matrix in the following. We stack all these point pairs into the matrix chi. So these are all the data that we have in the 2D images. And then we find the vector E stack that spans the null space of that matrix. And how do you typically find the null space? What you do is you do a singular value decomposition of that matrix chi, and then select the vector that in the matrix V chi that corresponds to the last to the 9th column of V. That is the smallest singular value. And so just using a singular value decomposition, we get the vector ES that we can then unstack into that matrix E. That is then an estimation of the essential matrix from the point correspondences, and now we project this down to the essential space. And what I mentioned is, in practice we do a singular value decomposition of that estimated matrix and replace sigma 1, sigma 2 and sigma 3 by 1, 1, 0. So first estimate the null space of chi, that is the matrix E. Then project down, meaning replace the singular values of E by 1, 1 and 0. So then we have assured that the matrix E really is an essential matrix. And then read out rotation and translation in the way I showed you. I mentioned there are 4 possible solutions depending on whether you take E or minus E, meaning you have then 1s or minus 1s on the diagonal here. And that gives us 4 solutions, and in practice it means the rotation can be either rotation by plus pi over 2 or by minus pi over 2, and here similarly. So we have 2 possibilities for translation and 2 for rotation. And I wrote it again, the rotation around pi over 2 is plus 1 minus 1 here. The rotation around minus pi over 2 is just a transpose of minus 1 plus 1. And so this gives you a recipe to, we have until 11:45. This gives us a recipe to solve the reconstruction problem from 2 images, looking at 8 points in the two images. The question that already came up earlier, do we really need 8 points? This algorithm, linear algorithm, needs 8 points to make sure that the kernel of that matrix chi is really one-dimensional. So you need at least 8 points to impose that constraint. In practice, you can get away with fewer points. For example, what you can do is you can use the knowledge about the essential space in order to get away with fewer points. What you do is you, let's say, take 7 points, and then you have a 2-dimensional null space. I mentioned if you have 8 points in a non-degenerate configuration, you get a 1D null space, so a unique solution. If you get only 7 points, then that matrix chi has only 7 columns, and so the rank is at most 7. And then you get a 2-dimensional null space. So let's say E1 and E2 are the 2 vectors that define the null space, the 2 essential matrices that span that 2-dimensional null space. Then you know the solution I'm looking for must be some linear combination of these 2. I know it's in that space. And now I know the last singular value of E, since it's an essential matrix, must be 0. Which means that in particular the determinant of E must be 0. And so you can say find a weighting alpha that defines basically the weight between these 2 directions in such a way that the determinant is 0. Meaning what I do here is I say I'll only work with 7 points, and then I get a non-unique solution, some linear combination of the 2 degrees of freedom here, but I will find the right combination by checking which combination gives me a determinant 0, which gives me a solution that is an essential matrix. And so in this way, this is fairly straightforward, and Krupa's approach is a little bit more involved, and in this, along these lines, essentially, Krupa proved in 1913 that you really only need 5 points in 2 images. And once you have 5 points, then you can recover rotation and translation up to finitely many solutions, like we've seen here in the 8 point. We have 4 possible solutions. Interestingly, once we have degenerate cases, and this was studied very intensively in computer vision, in particular in the 90s. When I started computer vision around 2000, that was a very active area. People were working a lot on epipolar geometry, on multiple view geometry, and so some of the things they looked at was the question is, what if I have the reconstruction problem, but I know that the camera is only translating? That can happen, for example, if you're in the movie industry, you fix your camera to a train and the train drives down a straight track, you know it only translates, there is no rotation. Can I use that knowledge to get away with fewer correspondences to constrain the reconstruction problem? What if I know that the camera is doing a circular motion? Or a planar motion, that my camera moves in a plane, that is no rotation, if it's a circular motion, etc. And it turns out, if you have additional knowledge, you can get away with fewer cameras. Something that came up recently is, I mentioned cameras in smartphones have inertial sensors. And so typically you can estimate the rotation of your camera. You may not know where in space it is, but you may estimate the rotation, or at least components of that rotation. And it turns out then you can revisit that problem and say, what if I have these parameters from my inertial sensors anyway? So I don't want to estimate them, I know them already. Then it turns out all these additional knowledge can be mapped to having fewer point correspondences. So rather than having 8 points, or rather than having 5 points, we can maybe get away with fewer points. Some last words about the 8-point algorithm. I mentioned there are 4 possible solutions for rotation and translation. In the general case, where I have 8 points, where I have a non-degenerate scenario, I have 4 solutions for rotation and translation. The question is, which one is the right one? The way you can easily check that is, you can take each solution and check what is the 3D reconstruction it gives me. And then you can check which one gives me positive depth values, meaning for which reconstruction are the 3D points actually in front of the 2 cameras. Because you know I'm looking at the scene, they have to be in front, and so you can typically easily rule out the wrong rotation and translation because it doesn't give you positive depth values. And the one that remains, the one that gives positive depth values, is then the right one. So that ambiguity that we have here, the fact that we have 4 solutions in practice, is not an issue. Another issue with this 8-point algorithm is that it fails if the translation is exactly 0. So if I take an image and then I rotate the camera and take another image, something that actually does happen in practice. If people are on vacation and they take multiple images and then they hope they can reconstruct the world, if the camera only rotates, if you don't have any translation, it's not good. Because then translation is 0, then the essential matrix is 0, and then you can't do anything. In reality, though, even if you stand still, that doesn't happen, because typically there is a little bit of translation, but you typically want to make sure that it's not too small, the translation. Another thing I should mention is that there is a version of the epipolar constraint, the so-called continuous epipolar constraint, which is the in the small viewpoint change, in the infinitesimal setting. Remember when we did tracking, actually, we said we would like small displacements to get reliable correspondence. What you can do is you can similarly formulate an epipolar constraint in the infinitesimal setting, and then it's a constraint that couples contains not rotation and translation, but the linear and the angular velocity of the camera, meaning the derivatives, basically. How does the rotation change? And that is the angular velocity, and the linear velocity is how does it infinitesimally move from one image to the next. And there is a similar constraint for that you can use. Maybe the last comment, we remember there was the epipolar constraint that couples the 2D coordinates with the camera parameters. What if we have a non-rigid scene? What if we have a scene where there are independent motions? For example, the camera is static, but the car drives through the street. Then the background moves with one rigid motion with respect to the camera, and the car moves with a different rigid motion. What you can do is you can use so-called factorization techniques. You can, here for example, you can use the fact that each 2D pair either fulfills one motion, which means this term must be 0, or it fulfills another motion, which means that term must be 0, with two different essential matrices. So we allow two rotations, two translations, we have two essential matrices, and we say we don't know whether the point is on the car or on the background, but no matter where it is, it either makes this 0 or it makes that 0. And so we can say we know for any point that we observe in two images, the product of these two must be 0. At a first glance, this is a bit nasty in terms of optimization once you have products. It's a little bit involved, but there are strategies. If you have enough points, you need more than 8 typically. If you have enough points observed in the two images, you can even estimate two motions, two rigid body motions, one for the car, one for the background. So I just wanted to mention there are techniques, polynomial factorization techniques, that can be used to tackle this generalized setting. Okay, we'll stop here, and next time we'll talk about how to extract 3D geometry. Now that we have the camera motion, how can we estimate 3D locations? Thank you.